Hello everyone, welcome to D Block Elements Lecture 2, and in this lecture we will be covering the reactions, like what reactions or reactivity can we expect from our D Block elements, what colors do they show in the aqueous medium, and what compounds do they form along with the uh, like reactions of those compounds and their oxidizing actions. Okay. So keep in mind the NCRT only mentions two compounds, so we will be covering only those two, and both of them are oxidizing agents. Watch this at 1.25x or 1.5x for the best experience and share to your friends if you can. So without wasting any further time, well, in the last lecture we studied about the trends of their E naught. E naught in the sense like what is their spontaneity when they are going from +2 oxidized state to their metallic form, and from their +3 oxidized state to their +2 oxidized state. So the spontaneity of these can be judged by the E naught of the cell reaction, and we can use this to predict their reactivity. Now, except for copper, all of them are oxidized by 1 mole of H plus ions. What does this mean? Well, we know, we studied in the earlier lecture, that if you gave copper the option to stay in either the +2 state or in the metallic form, copper actually prefers the metallic form unlike other elements of the 3D series. And this is the reason why it cannot undergo reactions like Cu plus 2 HCl gives CuCl2, because here it has gotten into +2 state, and from 0 it has gotten into +2. So this is an oxidation reaction, and we are told that except for copper, everyone can be oxidized by 1 mole of acid, but copper cannot. Okay, so keep that in mind. Now, all of them are sure oxidized by this acid, but reaction might be slow. Okay, for example, you might need more wilder reaction conditions, because titanium and vanadium, they don't react with a non-oxidizing acid at room temperature. What is a non-oxidizing acid? For example, look at HCl. If you look at its conjugate base, which is a chlorine anion, it is already in its maximum oxidation state and it cannot cause any more oxidizing action. Similar with H2SO4, we see that its conjugate base, like if both of these are gone, the conjugate base HSO4 2 minus, sulfur is in +6 oxidation state and it cannot provide any more oxidizing action. But for example, look at nitric acid and NO3 minus. In fact, KNO3 is a very good oxidizing agent. So NO3 is the real deal here, and this is a good oxidizing agent. Hence, HNO3 is regarded as an oxidizing acid, and it is not considered in this category. So titanium and vanadium don't react with non-oxidizing acids at room temperature. Now, as we move from left to right, the tendency to form a divalent cation decreases. What is a divalent cation? Why M2 plus? If you want to do this reaction from M, you want to go to M2 plus, you have to pay the price of energy by removing one electron and removing the other electron. So, as we go from left to right, the there's increase in the sum of the first ionization energy and the second ionization energy, and this leads to a less negative E naught for this exact reaction. In fact, this means that what is the spontaneity from going to minus from +2 state to the original metal state, and if it gets less negative, means that the metal now is starting to get more confused. Like currently it was very sure about staying in the +2 state, but if the E naught started getting more negative, it is now starting to get more confused about which option to pick. Okay, like we studied here. Okay, so if it is confused on which state it should pick, which means that if there is greater confusion, which increases left to right, the tendency to stay in this state without any issues decreases. And this is thanks due to the increase in sum of the first and second ionization enthalpies. Now, these points you have to remember by heart, they have been asked multiple PYQs before. In fact, even in 2025, multiple PYQs were asked from this single line of NCRT. The manganese plus 3 ion and the cobalt plus 3 ion are very strong oxidizing agents in the aqueous solution, whereas the chromium plus 2 ion, titanium plus 2 ion, and vanadium plus 2 ion are very strong reducing agents. And in fact, chromium plus 2 is the strongest reducing agent in the 3D series. Alright, and these are the strongest oxidizing agents in the 3D series. So keep that in mind. And a way to remember this is that somebody who has plus 3 wants to lose an electron to go to plus 2. But something which has a plus 2 wants to gain an. Wait, I said the opposite. This wants to gain an electron to go to plus 2. And something which has plus 2 wants to lose an electron to go to plus 3. So if they are losing an electron, they are reducing. And if they are gaining an electron, they are oxidizing. Alright. Take a moment and note this down. You will also get the PDF. Now let's turn about the magnetic property. First of all, some basic definitions. Diamagnets or diamagnetic materials are repelled by magnets. Paramagnets or paramagnetic materials are attracted by magnets. And ferromagnets or ferromagnetic materials are insanely attracted to magnets. Like, this is the face they make when they are looking at a magnet, and these are like iron, cobalt, nickel, and some other things I forgot. But paramagnets are less. Like, for example, the O2 gas is paramagnetic. If you pour liquid oxygen down to pointed magnets like this, it sticks like this. This stream of liquid oxygen is going to stick around the pointed magnets, whereas diamagnets, they are repelled by magnets. So this was the basic magnetic property. And one thing they can ask in an MCQ, the paramagnetism or ferromagnetism is caused due to presence of unpaired electrons. And the why do the electrons have their own magnetic moment? It is because of the spin quantum number. Like, if we consider electron to be a spherical entity, it is spinning about its own axis, and the orbital angular momentum. Spin formula, I don't think you need to know, but for this orbital angular momentum, there is a formula for the angular momentum, which is root subsidiary quantum number or azimuthal L into L plus 1 into h over 2 pi Bohr magnetons. This is the formula for the orbital angular momentum, and direct question from this has been asked in J 2025. Okay, and a Bohr magneton, it is basically 9.27 into 10 raised to power negative 24 SI units of magnetic moment, which you don't need to know for chemistry. The magnetic moment for our d block elements is given as a function of the unpaired electrons, and this function is the magnetic moment is equal to root n into n plus 2, where n is the number of unpaired electrons, and this number into this number will give you the magnetic moment in SI units. But in exam, you will most likely be asked it in Bohr magnetons, so remember it in Bohr magnetons. This formula is applied. Now, I want you to remember these values exactly. They are not too hard to remember actually. Well, titanium 3 plus has one unpaired electron. You can draw these configurations. We are not going to waste time doing that here. But using this formula, if the number of unpaired electrons is 1, we get 1 into 1 plus 2. So this is nothing but root 3. Similarly, we have 2 here. So this is nothing but root of 2 into 4, or 2 root 2. Root 2, we know it is 1.42. So 2 into that is 2.84. Now this is the value of root 15, which you have to remember exactly 3.87. Why am I saying exactly? Because they asked the integer type, in which they did not allow any type of approximation to be made, and they told you what is the sum of, what did they ask? They asked the sum of this value and this value, but they, of course, they did not ask this directly. You were said that some ion has 3d3 configuration and one of them has 3d4. find their magnetic moments and add them, and the value is x into 10 raised to power minus 2. Now you know the meaning of this. This means your x must be accurate to the third decimal number. So for that reason I'm telling you to remember these values perfectly. It is not difficult to remember that 3d0 and 3d10 will give a 0 because no unpaired electrons, and 3d1 is going to give you root 3, 3d2 is going to give you 2 root 2, and 3d3, these are actually the only ones you have to remember. Root 15 is 3.87. Root if this was 3, we get 4 into 6. Root of 24 is 4.9, and for 5 we get a root of 35, which is 5.92. Okay, but if you don't remember, if you are dealing with MCQs, okay, if you're dealing with MCQs, there isn't going to be exactly a lot of an issue here, because say if you are doing n into n plus 2, you can approximate it to n plus 1. Okay, but this is only for MCQs. I'm still telling you, for integer type questions, remember these exact values. It is going to only help you in the long run. Okay, and credit to Mathongo for this data. I'm using their highlighted NCERT. Now this is the most irritating part of this chapter, but I have made it easier for you. But so we have to learn about colored ions. Now the D block elements cations, they are colored in aqueous solution. Why is that? You will learn about this more in the coordination compounds chapter, but I'll tell you a basic reason here. You know how there are d orbitals. If there are 5 d orbitals, basically when a ligand, what is a ligand? A ligand is basically something which can donate a lone pair of electrons to the central atom, which has this d orbital. So when the ligand is approaching towards the central atom to provide electrons here, what happens is that three of the d orbitals and two of the d orbitals, they undergo a split in energy because of repulsion via the ligand. So the in normal cases the Eg ones go up and the T2G ones they come down. So basically electrons are getting filled here. Now sometimes if you provide energy, this electron it can move from the T to the subshell to the Eg subshell. Now in structure of atom, you have stated that if from one shell an electron jumps to another shell and then jumps back, it is going to give out a wavelength, and in our case that wavelength just so happens to be in the visible region, and that visible region is going to be perceived by us using colors. Okay, this is what we call a DD transition, because one D subshell to other D subshell. Okay, this is what we call DD transition. And also they exist as complexes. Basically they will form entities like this in water, where water will be donating lone pairs to this central atoms D subshells. Okay, now these are the oxidation states and the colors you have to remember, but don't try to brute forces. I have brute force it. I will try to help you. Remove this. This is just a list of the colors. Keep see one thing, that SC3 plus, Ti4 plus and Zn2 plus are colorless. Why is that? Because this has a D0 configuration, this has a D10 configuration, and this has a D0 configuration. So there are no unpaired electrons which cause the color, because if you want a DD transition to take place in the first place, there must be free space here, which is not present in the D10 configuration, and in D0 configuration there are no electrons to jump. So these are of course colorless, but for the others we are going to learn a basic trick. Now these are the common oxidation states of these elements which we have to study, and I already told you about SC, Ti and Zn. So for the others you need to remember two things. Okay, from vanadium to copper, the +2 oxidation state exists, and there are exactly 7 elements for which you have to remember the colors of the +2 state. And from titanium to cobalt, there are 6 elements for which you have to remember the colors of the plus 3 state. Okay, so I have made separate tricks for plus 2 state and plus 3 state. For plus 2 state, you imagine that you and your brother, you have went to a shopping mall and you have gone there to eat food. So it's basically just when bro picks good pizza, good burger. That's it. And how do I remember the color by this? Well, the only thing you need to brute force into your memory is that this has 7 letters and hence 7 elements we are describing over here, and which is vanadium to copper. Okay, the plus 2 state of titanium and scandium does exist, but it's not that important. Okay, so using W, you have to remember V for vanadium and also V for violet, because you know W and V make similar noises. So violet you have to remember. Using bro, you have to remember blue. And this is in order of the elements. So you need to know the 3D series in order. You will go in this order. For example, if the second letter has bro, which is blue, which means that Cr2 plus is blue in color. Similarly, Mn2 plus is Pi or pink in color. I have wrote it as Pi because purple is written as Pu. Okay. G is just green, which means that Fe2 plus is green in color. Pi again for CO2 plus. G, which means Ni2 plus is green. And B, which means CO2 plus is blue. So when bro picks good pizza, good burger, you have to remember this order and this order. And this is just easy to remember now. For the plus 3 state, imagine that there is a girl, which is this girl, and she is very pure hearted, and her name is Vivi. She is very pure hearted, like very nice person she is, but you know, nice people they would have to work hard to get things in life. And basically yearns, what is the meaning of yearn? Yearns mean basically struggle, or it could mean basically waiting for something, longing for something to happen. Okay, so pure girl Vivi yearns badly, like she has to struggle a lot in to achieve her goals, because she wants to do them via pure and non-malicious methods. So using this, you remember the plus 3 transition states colors. How? You remember it starts, you have to brute force it into memory that it starts from titanium and ends at cobalt, the plus 3 states. Like normally plus 3 states exist for other elements too, like scandium, but we are only learning the colors right now. Okay, as the vanadium plus 5 also exists here, plus 6 also exists, but we are not considering their colors here. Okay, so using pure, you have to remember Pu, which means that titanium 3 plus is purple in color. Using gold, you have to remember G for green, which means vanadium 3 plus is green in color. Similarly, copper 3 plus is violet in color. Mn 3 plus is also violet in color. Your Fe3 plus is yellow in color, and your CO3 plus is blue in color. Okay, and lastly, there is only one guy for which you have to remember the plus 4 oxidation state. Vanadium 4 plus is blue in color. This is the only one which is not in the two series mentioned, and this is easy to remember, man. Four letters, just remember it, please. And for titanium, I explained to you how it is colorless. Okay, so that was it for the colors. Let's now talk about some of their abilities, the D block elements. The D block elements have the ability to form complexes. Due to their small size, high charge density as well, and their d orbitals, they can accept lone pairs from a ligand. Okay, and this allows them to form complexes very easily. And keep in mind some examples that CuNH3 whole 4 times is DsP2 and PtCl42 minus is DsP2. Okay. Now let's talk about catalysis. Thanks to their multiple oxidation states, like this, they are very versatile and they can adjust their oxidation state according to the need of the reaction. So they can do multiple oxidation states and form complexes which allows them to make really good catalysts. Now, there's a process called the contact process. I don't know what it is, but just remember that vanadium is used as a catalyst in that. And this can be asked in an MCQ. Vanadium is used as a catalyst here. Iron is used as a catalyst in the Haber's process. Haber's process you must know, like N2 plus 3H2 gives 2NH3. So iron is used as a catalyst here to drive the equilibrium to the right side. And you must have studied in organic chemistry that we use something called Raney nickel, which is finely divided nickel, to serve as a catalyst for hydrogenation, where we add hydrogen to a unsaturated carbon-carbon double bond to form an alkane. Okay, and this is the NCRT screenshot about why catalyst happens. Now, catalysts at a solid surface involve formation of bonds between reactant molecules and that of the catalyst. Okay, like this is the catalyst, and catalyst has atoms on its surface, and this is the reactant. Okay, so they form bonds, and this is basically an intermediate. If you would have gone from reactant to product directly, this must have high energy of activation. But in this state, it has low energy of activation, as this increases the concentration of reactants at the surface of the catalyst, and the product is really available to come and react with the reactant here. So it reacts with the reactant and the catalyst leaves out on its own. Let's see an example of this. Keep in mind that the activation energy is lowering because we are weakening the bonds of the reacting molecules. Now this is a direct PYQ in 2024 JEE Mains. The iron 3 plus catalyzes the reaction of iodide iron and persulfate iron. How? The third oxidation state of iron reacts with the second reacts with 2 moles of iodide iron to form a diatomic iodine atom, and when it when the persulfate ion reacts with the plus 2 oxidation state of iron, it forms the sulfate ion. Okay, and the overall reaction can be written as this, where if you add these reactions, this and these cancel out, and this cancel out. Okay, so that was it about catalysis. Let's learn about interstitiality. What is interstitiality? Basically, their crystal lattices is big, and they are bigger compared to the second period elements. So sometimes they allow small elements like hydrogen, carbon, nitrogen, also boron, lithium, to live in their lattice, like this, in between of their lattice, and this is called an interstitial compound. Now, what is the properties of an interstitial compound? First of all, they are non-stoichiometric. They can be stoichiometric. For example, Mn4n exists, but very usually they are non-stoichiometric. For example, VH0.56 and TiH1.7 exist, and they neither are ionic nor covalent. They have higher melting or boiling point than the pure metal, thanks to the strengthening of the crystal lattice by these atoms, and they are very hard, like the interstitial compounds in which there is boron in between here. They can approach diamond in hardness, and that is amazing because diamond is the hardest known substance on earth. They retain their metallic conductivity, which is a plus point because they are still able to conduct electricity just fine while having these guys in between. And lastly, it becomes chemically inert. Okay, so this was it about interstitiality. Now let's learn about alloys. I just attached the NCRT screenshot. Okay, alloy is basically a blend of metals prepared by mixing the components. Now, what is the difference between interstitiality and alloy? Interstitial compound is basically a large atom whose lattice is occupied by smaller ones. But alloy is basically, it's just the combination of two metals, basically a solid solution where atoms of different metals exist in the same lattice. Okay, this is an alloy. Now, they are homogeneous solid solutions. Homogeneous because all the elements are in the same phase, which is solid. And keep in mind that the metals which form these alloys, their metallic radii are within about 15% of each other, which means that If one guy has 100 pm radius, the other one must have 85 to 115. Okay. And unlike interstitial compounds, the smaller ones won't work here. So that is not an alloy. And because of similar radii, that's it, 15%, they are readily formed by these metals, and they often have high melting points. Okay. Now you need to remember these alloys. Brass is copper plus zinc, bronze is copper plus tin, and your stainless steel is basically iron plus chromium plus carbon. Yes, carbon also exists in a small amount in the lattice, but we are not calling it an interstitial compound because there are two atoms here, and chromium is the key element. Okay, so and there is this random extra point which was given to me in a question, that the sixth state of manganese disproportionates in acidic medium to the fourth state and to the seventh state. Okay, so that was it about the extra properties of D block elements and also the colors. So now we learn about the oxides and oxoanions of D block elements. Now, how are these oxides formed? They are formed by the reaction of the metal with oxygen at high temperatures. And except for scandium, all MO exist. What is MO? MO basically वही FeO, CuO, like one metal atom and one oxygen atom. That is what MO means. But SCO does not exist because, as I told you, the +2 oxidation state of scandium is very rare and it's not stable in this way. Okay, and oxygen stabilizes the fifth state of vanadium by forming this guy, the fourth state by forming this guy, and the fourth state of titanium by forming this guy. You see they are similar. Okay, now you need to know these things. There was so much information here. I just attached the NCRT screenshot. Basically, you need to remember that Mn2O7 is a covalent green oil. Okay, and basically higher the oxidation state, the acidic character of the oxide increases. For example, what does it mean to be an acidic oxide? Like we learned that if CO2 dissolves in water, it forms carbonic acid, which dissociates as an acid into H++, the bicarbonate ion. And this means that if dissolved in an aqueous medium, they make an acid. Hence, CO2 is regarded as an acidic oxide. So similarly, if we dissolve Mn2O7, I mean it is said here that in higher oxides, acidic character is predominant. And Mn2O7 is a covalent green oil. Okay? And remember that CrO3 and V2O5 have low melting points. Extra points, they can ask anything. Mn2O7 gives HMnO4 in acidic medium. Sorry, in aqueous medium. HMnO4 is called manganic acid. Manganic acid. And this is a strong acid. Not mentioned in the NCRT, but still I just told you. And CrO3, which is the sixth oxidation state of chromium, it dissolves in water to give H2CrO4 and H2Cr2O7, both of which are decent acids. Okay, but V2O5 is amphoteric, although it mainly acidic, and it dissolves into VO4 3 minus as well as VO2 plus salts. Okay, you need to remember that V2O3 is basic, V2O4 is less basic, and V2O5 is amphoteric. And you need to remember these two things, that V2O4 dissociates into acidic medium to give VO2 plus, and V2O5 in basic medium gives VO4 3 minus, and in acidic medium gets VO4 plus. Okay, and again these are oxide behaviors you have to remember. V2O5 is amphoteric, V2O4 is less basic, V2O3 is basic, while chromium oxide, like +2 oxide is not +2, chromium +2 oxide is basic, chromium +3 oxide is amphoteric, and chromium +6 oxide is acidic. As I told you, when you go down, I mean go higher in the oxidation states, the oxides start getting more acidic. Okay, again great to Matango. So that was it about the entirety of the D block elements. But unlike P block, we also have to study the compounds. But luckily for you, there are only two compounds, potassium dichromate and potassium permanganate. So let's quickly wrap those up. Now you need to know the methods of preparation of potassium dichromate. Luckily, there is just one. You have to start with the chromitor. Chromitor is basically FeCr2O4. You start with this and you react it with sodium carbonate. You remember in salt analysis we studied something called sodium carbonate extract, because these guys, they can cause displacement reactions and make something which is suitable for testing. Well, here something similar takes place. We react your chromite ore with sodium carbonate and displacement reaction takes place where Fe2O3, I mean something with Fe and CO3 is formed, what it breaks down into these two. But the main part is that Cr2O4, it combines with Na, okay, to forms Na2CrO4, which is sodium chromate. Sodium chromate. Now this exact reaction, it would be nice if you remembered it, okay? But if you have less time and don't want to, just leave it. But just so you know, this came in my shift. So I would recommend again skipping it. Which was I guess 2S1 or something. I don't know, I forgot. But yeah. Well, one thing you can do to remember this is basically you can remember what conditions lead to this reaction. First of all, notice one thing, that the sum of the stoichiometric coefficients on the left side is 19, while that on the right side is 18. So this fact may help you in remembering the, basically if you forget the stoichiometric coefficients of one side, you can use the other side to remember it. This has some 18, this has some 19. I said the opposite, okay? And basically this reaction has to be done in the presence of an oxidizing agent, okay, which explains the presence of the 7O2 here. And note one thing, the it is said that the solution of sodium chromate is yellow in color, and as a general point, any chromate salt is yellow in color and any dichromate salt is orange in color. So the yellow solution of sodium chromate is bakwas with sulfuric acid to give a solution from which orange sodium dichromate can be crystallized. Now what does this mean? Well, I have only laid out a general formation reaction, but the actual reactions I have attached the NCRT screenshots, and let's take a look at them. The chromite ore reacts with sodium carbonate to give chromate in the form of sodium as spectator ions, and when it reacts with acid, basically a kind of dimerization, you can say, takes place. But it's not exactly a dimerization. It's just basically two CrO4 they add together, but not completely. One oxygen is left out as a food for this H plus. And yeah, this reaction happens only in acidic medium. And later you will study that in acidic, dichromate is more stable, but in basic, chromate is more stable. Okay, and basically these are they are interchangeable. Okay. So that's what happens here. The chromate ion changes to the dichromate ion, and we are using Na2Cr2O7 so far because sodium dichromate is more soluble. And if we react that with potassium chloride, you know potassium is more reactive than sodium, so it displaces sodium and finally forms our dear K2Cr2O7. So these reactions you have to remember. Please don't skimp on them. And let's look at the properties of KMnO4. Chromates and dichromates are interconvertible in aqueous solution depending upon the pH. Acidic is dichromate more stable, basic chromate is more stable. And oxidation state of chromium in both is same, both is +6. Okay. Now let's learn about the properties of the chromate and the dichromate ion. First of all, this excerpt from the NCRT. Both of them are tetrahedral in shape, but the second one is actually two tetrahedrals joined with one single O atom in between. Okay, this was the dichromatan and chromatin, and they have asked the previous year question on this, that are all the CRO bonds in dichromatan equivalent? And the answer is of course no. The middle ones are longer, which means that these are weaker bonds compared to the outer CRO bonds. Okay, and as a fact, just remember that this angle is 126 degrees. Okay, and here this is a perfect tetrahedral structure. So, they are strong oxidizing agents in acidic media, and they are used as primary standard in salt analysis. Just remember this as a point. Just remember this statement: primary standard in salt analysis. I won't explain you the meaning behind this, but it has something to do with checking the quality of the titrant when doing titration. Okay. More importantly, what is the oxidizing action of the dichromate? This is the oxidizing action with N factor 6. And keep in mind, this happens in acidic medium only, as you can see by the H plus. Basically, the Cr2O7 minus, it reduces into Cr3 plus, and these are the side guys. The main thing we have to see, Cr2O7 minus gets reduced into 2Cr3 plus. And if you want to make the full reaction with anything that can be oxidized by the oxidizing agent, these are the half reactions. Okay, and I think you know enough redox reactions to make a full reaction from these. If you don't know, you can just leave preparation. Nahi, I mean, if you don't know, you can just basically add these reactions. Okay, now potassium permanganate. What is the potassium permanganate? This is slightly more complex, but we'll do it. How is it prepared? Remember this statement: direct PYQ came. Fusion of manganese dioxide with a group 1 hydroxide like NaOH or say KOH. So if you fuse manganese dioxide with this group 1 hydroxide under an oxidizing agent, and NCRT specially mentions KNO3, this will form MnO4 2 minus. How? Here oxidation state of manganese is 4 and here it is 6. The V and I exchange positions. So oxidizing agent KNO3, it made plus 4 state into plus 6 state. Okay. And this MnO4 2 minus, remember we studied something earlier. We studied something. The plus 6 state disproportionates in acidic medium to give to give Mn4 and Mn7. So the same thing happens here. When we form this MnO4 2 minus, it disproportionates into MnO4 minus, which is the permanganate ion, and this is just the manganate ion, and gives back manganese dioxide. Now remember the colors. K2MnO4 is dark green. MnO2 is brown black in color, while KMnO4 is dark pink. In fact, it is so dark pink, like from a distance, you will feel it is almost black. I don't think I can show it to you on the spectra. I'll, like, this is pink, and you can say around this is the color of the potassium ion. Potassium, what am I saying? The permanganate ion, like around this color, this around this. Okay, so going back to our laser, KMNO4 is dark pink in color, and let's learn the NCRT stuff. As I told you, prepared by fusion of manganese dioxide with an alkali, yani group 1 metal hydroxide, an oxidizing agent like KNO3. This produces dark green K2MnO4, which disproportionates in a neutral or acidic medium. The disproportionation, as we know it, we learned it earlier also. It happens in acidic medium, but they're also saying it happens in neutral medium, so remember that. And this basically it gives permanganate. Okay, but commercially, we use it. We make this guy by alkaline oxidative fusion. Now, what does this mean? Just remember the words alkaline oxidative fusion. If they're saying oxidative fusion and electrolytic oxidation, you can also do it in an alkaline medium. Like here we did neutral and acidic, but if you want to do this in alkaline medium, you can also do this via oxidative fusion of MnO2 and electrolytic oxidation of manganate 6. Okay, I think this is the exact same process though. Alkaline oxidative fusion. This is the exact same thing, I guess. Electrolytic oxidation. Hmm. Ignore what I said. Now, in the laboratory, this is an alternative method of preparation, but not much has been asked from it. Just remember, the second state of the manganese ion, it is oxidized by peroxo disulfate. This guy, peroxo disulfate. And basically, this oxidizes your manganese 2 plus ion into the permanganate ion. Okay, so and itself gets reduced to whatever this is. Okay, now potassium permanganate forms dark purple, almost black crystals, which are isostructural with those of KClO4. Basically, they are saying this structure, this structure is similar to that of KClO4. What can be the structure of KClO4? Chlorine has 7 lone pairs, 7 free electrons, so I guess this must be the structure. So I can see the similarity actually. These are isostructural. So KClO4 is a good analogy to remember the structure of the permanganate ion. This salt is not very soluble in water, but if you heat potassium permanganate, it will decompose into K2MnO4, the manganate ion, and the MnO2, manganese dioxide, which was brown in color. Okay, remember this, the green and purple part, and look at these structures carefully. Now, it has physical properties of considerable interest. It has intense color and it is weakly paramagnetic, and its paramagnetism is temperature dependent. And this can be explained on the basis of molecular orbital theory, but they have said that this is out of the awkaat of the NCRT. So don't concern yourself with the reason. Just remember that the permanganate ion has weak temperature dependent paramagnetism. Okay, and the green manganate ion is paramagnetic, while the permanganate is diamagnetic. Like what we studied here was for the manganate ion. Okay, and the pi bonding takes place by overlap of p orbitals of oxygen with d orbitals of manganese. Basically, they are saying that this is p pi d pi bonding. Keep in mind they can ask this because it sounds important. Okay, they can ask what kind of bonds are present in the permanganate ion. So they can ask p pi, p pi, p pi, d pi, d pi, d pi. Okay. Now let's learn about the oxidizing action of the permanganate ion, and it has three different oxidizing actions. In purely acidic medium, there is large concentration of H plus, and basically the oxidizing action of this guy is dependent on the concentration of H plus. And as a general point, I'll write it down. In acidic media, it goes from +7 to +2. In neutral or weakly basic, it goes from +7 to +4. Here was +2. And in basic, strong basic, it goes from +7 to +6. Like in strongly basic, there is low amount of H plus, so it's not able to change much of its oxidation state. And again, you can use these half reactions to make the complete reaction once the other reducing half reaction is given to you. And remember, the n factor here is 5, here is 3, and here is 1. Okay, So that was it about the D block elements, and we have completed the entirety of this chapter. F block elements come soon, and it will be done in one lecture. So that was it. Thank you for sticking around, and drop a subscribe if this helped you. I am providing the notes in the description and the pinned comment. Thank you.